So this is our official start of big data. Share my screen, come back over here. And so today in class, what we're going to do is finish up our discussion of the different strategies, algorithms that can take advantages of index. We've talked about the different table scanning strategies, and last time we talked about some sorting strategies, ending with the idea of sorting explicit sorts is bad. We want to use an index to sort whenever we can, and the reason that we can do that is because in these B+ trees that Postgres uses, they have these links between all of the nodes at the same level. And so as soon as you find one thing, you can just continue traversing to get everything in a sorted order. And this is going to work for any sort of index scan or index only scan, will not work for the sequential scan or the bitmap scan. Let's see, one other thing that I wanted to go over last time, but I forgot, just this quick idea again of we're using this Russian website and Russian people not being particularly nice right now. Why are we collaborating with them? This Arthur Eddington is one of my, another one of my sort of personal heroes. He was the only person during World War I who continued collaborating. He was an English person, but he continued collaborating with the German scientific establishment, and in particular with Albert Einstein. And it was because of that collaboration that we got our first actual empirical evidence of general relativity during this solar eclipse right here. And if he hadn't done this, if he hadn't been in a position working with Einstein during World War I, then the next opportunity for this empirical observation of general relativity would have been in 1937, so a full 20 years later. But because people at war were collaborating, we got those scientific advancements earlier. And so by working with these Russians, even in this indirect way, we'll get our scientific advancements earlier as well. Last time where we ended off was, so this is the PDF file for our notes for this section of the class. And we ended up on this problem 6 right here of creating an index that's going to take advantage of a whole bunch of different things. So in particular, using an index-only scan, avoiding an explicit sort, and taking advantage of the limit clause. In general, for most of the stuff in this class today, I'm going to go really fast. I'm probably not going to stop explicitly for questions, just because I think most people are connecting or going to be watching this on YouTube. And so if you do have questions, either in class or on Zoom, just feel free to shout out and interrupt me. Otherwise, I'm going to plow through the material. So in this case, we need it to be an index-only scan. So we have 3 columns here that we know that we're going to need to mention: the id tweets, created at, id users. And we'll start off with the create index command on, and this is the tweets table, so tweets. And then the order is, again, the thing that's going to matter here. It's the order that's going to let us have an efficient query. And anytime you have the order, you want to go from the most restrictive to the least restrictive of the conditions that you're using. So in this case, the most restrictive thing is this equality constraint right here. So we start off with the id users. And then that leaves the id tweets in the created at column. In order for the order by to happen, the created at column will have to happen before the id tweets. So whenever you have the order by, that's sort of more restrictive than nothing, but less restrictive than an equality constraint. And so the next would come created at. And then the last one, id tweets. I'll make sure I have room, put it down here. And again, the id tweets not strictly necessary here for speeding up these conditions, but by including it here, we can do an index-only scan. If it were not included here, it would be only an index scan that we're able to do. In either case, an index scan or an index-only scan, we're able to take advantage of the limit clause. The only situation where we cannot take advantage of the limit clause is when we use the bitmap scan. And here we've created this index in such a way that we're not relying on a bitmap scan, so we'll be able to take advantage of this. So that's the correct answer for this problem. The next two problems, so problem 7 right here. This is a little bit different, involving a unique constraint. And I'm not going to do this problem explicitly for you, but I'm going to tell you that what you'll need to look up in order to do this problem is how to create a unique index where there are some columns that are not part of the uniqueness, that don't have a uniqueness constraint added to them. So here we have the created at column and the username column. And it's asking that the username column right here have a unique constraint, but the created at column not be part of that unique constraint. So the sort of semantics of that is in the users table. We only want to have one username at a time. It's not one username per millisecond that user's been created at. And so in order to do this, you'll have to look up the include clause of the unique index in order to get that to happen. So I'm not going to write out the full answer here, but this is what you'll need to look up in order to get the answer. Otherwise, it's the same as what we've seen before, and including both of these two things in the index. The next problem, also one I'm not going to complete for you, but just give you some advice on. So here there's a lot of different constraints going on and multiple different things being ordered by. And so you have to make sure that you get all of the orders for that you put the columns in correctly. And in particular over here, you can see that the order by has one order by is ascending and one order by is descending. And so you'll have to look up how to take advantage of that, how to make your index take advantage of ascending versus descending. So again, I'm not going to tell you exactly how to do that. You'll have to look up the ascending versus descending aspect of order by on indexes. And again, the references for looking all of these material up are linked on the notes this week. Why is that not going away? Well, so what we're going to, there's two more types of strategies that we need to look at today, and then we'll be done with these different strategies. The first one is aggregate strategies. So that's anytime you see the group by clause, or if you have an aggregate function like a count or a sum or a max anywhere in your query. And we've seen in our SQL queries that those two things sort of go hand in hand. This reference is what I'm going to go over in class. It's a presentation that sort of has a visual representation of these two algorithms that we'll see, the group aggregate and the hash aggregate functions. If you want to see it out in written form, though, that's this second reference right here. I'm going to switch tabs over here. So this presentation, again, is that first link. And there's a lot of slides in this presentation. They're all very interesting, but I think it's like slides 14 through 20-something that we're going to take a look at. And so again, two algorithms for these aggregate functions or grouped data, the group aggregate and the hash aggregate. And we'll have some animations here that will go through these and show exactly what's going on. So this first one is what the group aggregate function looks like. Over here to the left, you see that we have some data, and the data is somehow already been sorted so that the thing that's being grouped by are all together. So in this case, the group by is going by colors, and there's just some individual numbers in here, and they're trying to run a summation on these numbers. So we're trying to count how many blue numbers there are, or total up all the green numbers and total up all the red numbers. And so if we step one spot through this slide, here, what they've done is they've gone through and it's basically a for loop that's looping over all of these numbers here, considering each one at a time. So going from this line here to this line here has been 2 iterations of the for loop, adding this 1 and this 2 together to give us 3. And so in this blue state right here, we have 3. In the next iteration, it's going to add this 3 right here. That'll be the very last of the blues. And then it will have 6 in the state. It's also gone through a little bit of these green ones right here, considered both these first 2 green ones, the 1 and the 3, to give us a state of 4 so far. And then it has these 2 other green ones left to add. And so we get 8 as the final of our green states. And then on the red down here, it's going to add all those red ones together and give us the 5 as the output. The main thing to notice about this group aggregate is that, so the data must be coming in inside of a sorted order somehow. And so if we're using the group aggregate, then either we need the explicit sort to have happened previously in our query plan, or we need to have an index that we can just traverse to get things in sorted order. Another nice thing about the group aggregate that we'll see is that as soon as it's finished with one of these things that it's grouping together, it can immediately output that and we can get the result. So if we had, say, a limit clause, we're able to stop processing earlier. Or if we're in Python, we can start getting the results and processing them in Python before the Postgres query is even finished running. So that's the 2 advantages of the group aggregate. The next function is the hash aggregate. And here you can see that, so it's the same data over here that's being input. It's just now in an arbitrary order, non-sorted order. And when the data comes in, it's still going to be a for loop, considering things 1 at a time. So here, it just considered this first 1, added it into the blue state. So now we have a 1 as our summation so far. And then when we get the green, now it's going to just add another state variable that it's keeping track of. Green has 3 in it. Do the red one next, and it goes a handful of ways, adding things 1 at a time. So the state increasing, blue 6, green 6, red 1. At this point, we're done with blue, but the algorithm doesn't know that yet. It has no sort of future knowledge about what might be coming. So there might be some more blue ones over here, but we can't know that, so we can't output it yet. And we have to wait till everything's all done. Then here's our final hash, and then we can output these actual rows and get them out. The main takeaways from both of these 2 algorithms are summarized in this table right here. This is the thing that you really need to know. If you understand, I think, those previous algorithms, then this result right here, this summary will be intuitive. But this is the fundamental thing that you'll need to know to answer the problems for the final exam. So the group aggregate, the main downside is that it requires sorted data, but everything else is a plus. Needs less memory, returns the data in sorted order, might be useful for downstream operations. Again, returns the data on the fly, can be used for count distincts or a card, and it'll work on disk if need to, if it's a very large item or a large problem. The hash, though, advantage accepts unsorted data, but then everything else is the opposite. It needs more memory, returns unsorted data. You have to wait till the very end to get the data out, and only perform basic aggregations like sums, maxes, can't do these distincts. And it can result in this out of memory, in which case you'll have to do the group aggregate anyways and do an explicit sort so that you can do the group aggregate. Yeah, let's see. One, I'll just go up to this next slide right here that's comparing their in practice performance of these 2 implementations. So the hash aggregate here, the blue, the red is the group aggregate with an explicit sort. And so because there's the explicit sort necessary for the group aggregate, you're getting this It just takes a lot more time to do the sort plus the group aggregate. If we were, like, the vast majority of this time right here for the red line is the sorting step. So if it was just the group aggregate, then it would be smaller than the blue line. And then, yeah, the rest of these slides go through various performance optimizations to show you how to make that red line below the blue line, but that'll take us too far afield. So I'm not going to go over that explicitly. Yeah, so that's the aggregate strategies. These, what I've listed here is just that summary of the last slide. So again, the main things to know about the aggregate strategies, because these will be the things that you'll explicitly need for the exam sort of questions. The main thing for today is these join strategies. And these join strategies, I think, are definitely the most confusing of the sets of strategies that we're going to see. And they're also potentially the most important. So if I had to rank them in importance, the table scanning strategies are definitely like the most important, because every query is going to have this sort of format inside of it somehow. And so getting your right table scanning strategies is going to affect every query that you might run. And then after that, the join strategies are going to be the most important, because as we'll see, they can have really, really big impacts, going from quadratic down to linear or even sublinear. So these strategies used for any type of join, so in particular cross, inner, left, outer, full joins, all the different types of joins that we've seen, can be implemented with these join strategies. And as a note, sort of traditionally, joins are thought of as slow operations. And because of that, the standard NoSQL databases like MongoDB, CassandraDB, they don't have support for joins. And that's an intentional design decision in order to ensure that their operations are fast. But what we'll see is that if you have like an actual good understanding of these join strategies, then you can ensure that your joins are fast, and you can represent your data in a normalized fashion. Again, the normalized data sets will need joins to combine things together. MongoDB, Cassandra, all these NoSQL sort of databases, they represent things in a denormalized fashion. And so that's why they don't need to support joins, because the data is already sort of joined together. It's already denormalized. Postgres documentation, for whatever reason, doesn't have really good descriptions of these join strategies. And so this is, I think, the best link that I know of with the most, I don't know, succinct description of the strategies. And so that's our reference for this section. Okay, so for join strategies, there's 3 basic types, but we'll see that under those basic types, they have lots of different variations. The first basic type is the nested loop join. And this works sort of in all possible scenarios. The nested loop join has 3 variations. The first variation is if there are no indexes available, then the pseudocode looks like this. And you see there's 2 nested loops inside of each other. And so that's why we have the nested loop join. The idea is that, so just for each row in A, consider each row in B. If it satisfies the join condition, then we output that row as into our final, into our output table. For notation-wise, talking about runtime, we have 2 different tables now, A and B. And so I'm going to refer to the size of table A as, so the number of rows in table A as m, and the number of rows in table B as n. At least for me, it can be sometimes confusing to keep track of like m and n, what do they actually correspond to? But the way to remember this is that it's alphabetical. We have 2 tables, A and B, and then the m is alphabetically before n. So the m corresponds to the number of rows in A, and the n is alphabetically after, so it corresponds to the number of rows in B. I think this is sort of like the most obvious way to implement a join, and And it's, I think, relatively obvious how it gets its name of the nested loop join, because there's two nested loops here. And because this works in all scenarios, this is sort of the default. If you don't have any indexes, this is probably the sort of join that you're going to be using. And it has a really slow runtime. It's quadratic. And so that's why people who aren't really like intimately familiar with join strategies and indexes have an aversion to using joins, because they'll be using this type of join, and it is just inherently a really, really slow join. So yeah, basically what we're going to be doing in this section is figuring out ways that we can make this faster, reduce this runtime right here. The first modification that we'll consider, the first thing that we'll consider is, what if we have an index on B? And in that case, rather than doing like this for loop right here is essentially a sequential scan over the B table right here, so that sequential scan strategy, and to find rows that match this condition. But we can replace that with a different one of our table scan strategies, either an index scan or a index-only scan or a bitmap scan as appropriate. And the resulting pseudocode looks something like this. When I say find rows in B satisfying the join condition right here, that means that we're using one of the index scan methods. We saw before that those index scan methods have relatively complicated runtimes. I'm simplifying all those runtimes down here, ignoring things like the branching factor and how many results we're getting, so that it's only in terms of the number of rows of the table. And so the main important thing is that we go from a linear dependence on in, the number of rows in B, to a logarithmic dependence on in, the number of rows in B. Again, it's still nested though, one inside the other. So you multiply those runtimes together and you get m log n. Significantly better than the mn up here. Another advantage of this type of join strategy is that if we had a limit clause, it will take advantage of that clause. So here, if we have a limit k, then as soon as we've gotten our k different result rows, we can stop the for loop and break out and not continue doing anything else. So assuming that each row in A matches exactly one row in B, which is not always the case, but is a fairly common situation, then we'll go through this for loop right here exactly k times. So this O of m will become an O of k, and the runtime will be reduced to O of k log n. So again, this is not guaranteed to happen, but it is a very, very common situation. And so we get this runtime. And in general, though, anytime we have this limit k clause, we might not get exactly this runtime, but it's going to be still be able to prune off this for loop right here and shrink the runtime down significantly. So this is sort of the right way to think about the runtime. It's O of k log n. I mentioned that there's 3 versions of the nested loop join. Nested loop join has 3 versions, one with an index, and then with an index on B, the inner loop. And then the final version is with an index on A, what was originally the outer loop up here. In order to take advantage of the index on A instead of the index on B, you should so recall that joins are commutative. Commutative meaning that you can switch the order of the operation and it doesn't affect the results. The main subtlety that you have to think about here is that A left join B is equivalent to B right join A, so you have to swap the lefts and the rights. But Postgres can do that for you under the hood. Again, the query processor subsystem is going to rewrite your join or rewrite your entire query into whatever it thinks is the most efficient version. So you don't have to worry about this. Postgres will take care of it for you automatically if it thinks it's an appropriate thing to do. And if it does that, then it's just swapping the order of the for loops and then using the index on A in the inner loop right here. So everything stays the same in terms of our runtime, but we swap the order of the ins and the m's, and then the limit k, we can go to O of k log m down here. The overall advantage of doing this, again, is that, and the way Postgres will decide whether to do this or not do this, is it'll look at these asymptotic formulas, plug in the estimates that it has of all of these different numbers, sees which one is smaller, and then decide which algorithm to use based on that. So here, O of k log n versus O of k log m. If n is smaller, so if n corresponding to b, if the b table is smaller, it will use this strategy down here. If the a table is smaller, it will use this strategy up here. So that's the nested loop join, the 3 different variations of that. The next most general join is the hash join. And the main requirement, so again, the nested loop join has no requirements. It works in all scenarios. And in particular, it works under all possible join conditions. We saw a long time ago that your join conditions can be, they're usually equalities, so like one row equals another row, but they can also be inequalities, so like one thing less than or equal to another row. And the nested loop join will work for inequalities. For the hash join, however, it will only work on an equality condition. So this is, again, 99% of joins, every join that we've done in class has been an equality condition. Most joins will satisfy this condition, but not all joins will satisfy this condition. There's no indexes required in order to do a hash join. There is this special parameter, though, called workmem, that your hash table must be able to fit inside this working memory parameter. By default, this value is 20 megabytes. And so if you have a relatively small table, you'll be able to fit inside this value right here and do a hash join without any sort of indexes. What the pseudocode for a hash join looks like, so there's the first step is you build a hash table on the join column of B. It takes linear time to construct a hash table. And then for each row in A, you'll just check, is the join column in the hash table? Hash tables only support equality checks, and so that's why the hash join only supports the equality join condition. And because hash checking is, you might have a hash collision, you'll have to recheck that you actually are equal to each other. And if there is no collision, then you output the corresponding row. The runtime here of m plus n, so this is significantly less than for the for the nested loop join, because nested loop join was a product, m times n. This is a sum, m plus n, so significantly less right here. But there is a very large constant factor overhead. Building a hash table turns out to take a relatively long amount of time. Hash functions are relatively expensive. And so for large tables, for small tables, this overhead can dominate, and the asymptotic m time n could still be slower, m time n could still be lower than m plus n because there's a large constant factor here. Again, due to commutativity, we can swap the order of the B and A, so we could build the hash table on A if we wanted, and then loop over B if we wanted, and Postgres will determine that for you automatically, not something that you have to worry about. It'll know which one of those is more efficient and do the optimal choice. And then the last thing with the hash join is that it can also take advantage of the limit k clause. And in order to do that, we still must build the full hash table over here. So this does not get any performance increase at all. But this for loop, again, can early terminate after k iterations. And so we would get n plus k right here of k plus n. Or again, due to commutativity of k plus n. And again, Postgres will determine which one of these two is best for you automatically. Vast majority of situations, these two numbers right here are going to be smaller than these numbers right here. But that's not necessarily going to be the case. When n is extremely large and k is small, then these numbers right here will be faster, they'll be smaller. And so the nested loop join will be faster when the size of the tables is very large and you have an index. The hash join will be faster when you have no index available at all, because you'll get the plus instead of the product in your runtime. The final merge strategy, the merge join. The way to think about it algorithmically is it's like the merge step in a merge sort. So what it requires is that our inputs be sorted. So typically coming from an index or an index-only scan, or again, possibly from a group aggregate, but not from a hash aggregate. If our inputs are not sorted initially, then we'll have to do an explicit sort, which would, we've seen the algorithms for explicit sort. They're relatively slow, so we want to avoid the explicit sort. So the merge join really is only going to be selected if the inputs are already sorted because you're using an index somehow. The merge join, like the hash join, requires an equality join condition. So if for whatever reason you're joining on something that's not an equality, you will have to use the nested loop join. You can only use the other strategies on an equality condition. The advantages of the merge join. So again, if the data is already sorted, there is no setup overhead, so it has a very, very small constant factor. And we'll see that the early stopping is extremely, extremely efficient. So here's the pseudocode for what the merge join looks like. Again, this is the same pseudocode as the merge step in a merge sort function. Your while loop going, you have two indexes, I and j, I corresponding to the A table, j corresponding to the B table, again, alphabetical order. Lowercase a corresponds to the current row in the big A table, lowercase b, the current row in the big B table. If they satisfy the condition, then output it. Otherwise, increment either I or j, depending on which one's smaller. The while loop itself, we have to loop through, if there's no limit clause, we have to see every single row in both tables. So that's why we get the m plus n overhead right here, or the m plus n runtime. But it's a very small overhead. There's no hashing. Hashing, again, is the expensive step of the hash join. And so the choice between a hash join and a merge join, even though they have the same asymptotic runtime, we would always want to pick the merge join instead of the hash join if we can, because it has this small overhead. But really the most key important thing about a merge join is that if you have a limit k clause, then the runtime is just O of k. Doesn't depend on the overall size of either of the tables at all, because this while loop here, we never have to loop over the entirety of either table. It's just going to stop after we get the k elements, not having to look at the entirety of either table. So this is by far the fastest of the runtimes that we've seen, and best case scenario for any type of join operation, and it's always what we should be trying to achieve when we're building indexes. So again, the way that we would be able to achieve this, we have to ensure that our inputs are coming in sorted, and so that will mean that we'll have an appropriate index or index-only scan that is generating those things in sorted order. See, I will pause here for questions if anybody has them before going to the notes and seeing how this relates to the questions. Jody.
Curious what a hash collision is.
Question is, what exactly is a hash collision that is mentioned right here? And so the answer is that when we, I'm going to open up Python real quick and make this a little bit bigger. So Python has a built-in function called hash like this, and it just generates basically a random number. But the key idea of it is that that number is the same for every input. And if we change this input at all, we're going to get a different sort of random number right here. And in the hash table, the way the hash table is going to work is that we'll have some fixed size of our hash table. Say like there's 100 elements in our hash table because we expect there to be about 100 entries in the table that we're doing the join over, then the way the index of this value right here will be computed is by taking the hash, this big number, modding it by whatever the size of the table is, and that's the particular like location in the index that it gets stored at. And then a collision is when, so there's only 100 different possible of these values. There's a lot more than 100 different possible strings that I could pick. And so eventually I would come up with 2 different strings that result in the same index right here. And so in order to ensure that we actually do have a match, when the hashes match, we have to compare the actual values and not just the hash values. Does that make sense? Answer the question? Good question. Any questions from Zoom before we move over?
Yeah, I was gonna ask what are the values associated with the like hash, like what's the hash table like mapping?
Like how does it compute the hash function?
No, I mean like the hash table is like when it's created for a column, right? What are the like keys and the values like in that hash table?
So the question is here with this hash table, what exactly would be the keys and the values in this hash table? So if we have our join on whatever our join condition is, so if it's something like we have from A join B on A dot column 1 equals B dot column 2, then the hash table will be, let me adjust this right here. The hash table will be built on B dot column 2. So the keys in the hash table will be hash of B dot column 2 for each of the different rows in B. And the values of the table will be the TIDs for that particular row, so that we can check to see do the hashes match. If they do match, then we have the TIDs of the corresponding rows. From those TIDs, we can look up whatever other information we need about the rows. One thing that we will definitely have to look up is the actual value of b.call2, because we don't have access to that. But we might also have to look up, for example, like if the select statement has other columns. So if it was select b dot column 3, then we'd have to look up b dot column 3 as well from this TID. Did that answer the question?
Yeah, thank you.
Good questions. Any other questions? Okay, so in terms of the notes over here, the first way that this is going to come up is, so we have a very relatively simple query right here. We're joining tweets mentions on the tweets table using this particular column. Is column name is shared between both tweets mentions and tweets, so that's why we can be using the using syntax instead of the on syntax. Anytime you have a join, whenever there's a join, there will be multiple tables. And indexes exist only for a single table. So this is going to imply that you're likely to have, not necessarily, but likely to have multiple indexes. If you have no join, then the query can be answered with just a single index. But if you do have a join, then you're likely to need multiple indexes to get the most efficient query. And in particular, in this case, so it's specifically telling us that a merge join is being used. And so in order to make the merge join as efficient as possible, we need to make the input into the merge join sorted. So our goal is make the input into the join sorted. If the input is not sorted, then it would have to run an explicit sort step that's in login, which is super expensive. If the input is already sorted, then that in login gets replaced by an O1, because we don't have to sort it all. We just use the index and traverse whatever we need. So in order to make the input join sorted, we have this id tweets right here. This is the column that we need it to be sorted by, because that's what the join condition is. Recall that if we expand this out, that's equivalent to tweets underscore mentions dot id tweets is equal to tweets dot id tweets. And so anytime you're using the using syntax, you know you're going to have an equality constraint, so you know something like a merge join is possible, or a hash join would also be possible. And again, so these are the two things that we need sorted. Since those are the two things that we need sorted, we can do a create index on tweets underscore mentions of id tweets like this, and another one of create index on tweets of id tweets like this. And if we had these two indexes, then the query planner could choose to just traverse these two indexes to get the id tweets in sorted order, and then do the merge join on those resulting TIDs. We're not quite done with this problem though, because we need to, it's specifically telling us that we should not create any unneeded indexes. And so we need to check, do we already have indexes that match these two indexes right here? We'll first look at this bottom one, create index on tweets, id underscore tweets. Scroll up to problem 1, where we listed the indexes that were actually being created. So here's the indexes that have already been created. And right here, we see that we have the create unique index on tweets, id tweets. This was created by the primary key right here on the tweets table. So this is a unique index instead of just a plain index. In terms of queries though, the fact that it's a unique index has no impact. The unique index is only used at insertion time or update time or delete time to make sure we don't violate constraints. So here, this index already exists. And so on problem 9 down here, we do not need to create this index at all. The second index right here, this will be a little bit more subtle for us to consider. It says create index on tweets underscore mentions, id underscore tweets. And so let's go back up to problem 1. And we don't have any index that exactly matches the that same pattern. The pattern that we wrote down of what we needed was tweet mentions followed by id tweets. Here, this index is id tweets, comma, id users. So this is a multi-column index, but we only needed a single column index. We saw that this multi-column index was giving us problems on a previous problem where we were trying to do an equality check on id users. And because id users was the second item in this column list right here, we were not able to do that. But because id tweets is what we're looking for, and id tweets is the first item in this column list, we're able to sort by id tweets just fine. This index already contains all of the tweets in sorted order by the id tweets. This id users just means that it's breaking ties. If there happens to be multiple tweets with the same tweet ID, it's breaking ties by the id users value. So we actually don't need to create another index for this one as well. We don't need this index either. We already have sufficient indexes to use the merge join on this query as fast as possible. So run out of space, so I'll just go ahead and circle this as that's the final answer right here. If in problem 1 up here, if this primary key was reversed, so that it was id users first and id tweets second, then the corresponding index right here would not be containing the elements in order sorted by id tweets. It'd be containing them in order sorted by id users. And so we would not be able to do the merge join using this index. We would have to do an explicit sort. And so if these two items were reversed, then we would have to create that, that index in problem 9. Any questions about that problem 9? Okay. Problem 10, I'm not going to do explicitly for you, but this is similar to problem 9 above, but also combining the idea of needing a where clause right here. So you have to have an index that satisfies the where clause, an index that makes the both of these tables be able to be traversed in sorted order. And it is possible to do this with 3 indexes. It's also possible to do this with 2 indexes. So if this were like a final exam question, in order to get full credit, you need to be able to do this with just 2 indexes. I'll write that out. Number 11, similar, only now, rather than having you explicitly create indexes, you'll have to consider these indexes and what their different trade-offs are, thinking about what are the different possible algorithms that can be used. And then number 12, the idea here is now if we use not just the small tweets table, but the larger tweets table, what's going to happen is that our heap is going to be bigger. We'll be able to fit, write this out, heap larger, so fewer tuples per page. And you'll have to think about how is that going to affect, how is that going to impact all of my different algorithms. And it's going to specifically, yeah, like, so with a sequential scan, how many more pages are you going to have to access? Well, since there are fewer tuples per page and we have to access every tuple, the number of tuples here will increase. For an index-only scan, since we don't have to access the heap at all, the number of tuples will stay the same. And so you have to think about, for all of the different algorithms, how it's going to affect, how this property right here is going to affect them all. Back over to our notes. Yeah, Sally.
Oh, is it the number of tuples or the number of pages on that question?
Um, so this is specifically asking how the number of pages accessed is going to be affected. So the key property, the key thing that's going to happen, the tuple itself is going to be larger. So that means there are fewer tuples per page. And so if we're accessing the same number of tuples, then the number of pages is going to increase. But the number of tuples accessed will stay the same for everything. Does that make sense? Does that answer your question?
Yeah, because on the like sequential scan, you said the number of tuples will increase.
Oh, sorry. Thank you. That should be number of pages increases. For everything, the number of tuples stays the same. And yeah, here, it is also true that the number of tuples stays the same, which stays at 0. And here, the number of pages stays the same, which also stays at 0. Because the index-only scan is not going to access the heap. Yeah, thank you for that correction. Any other questions about anything at this point? Then back over to the notes. I have a quick comment about the join order. So up here, we're looking specifically at the joins just between 2 tables. But what happens if we have joins between more than 2 tables, like 3 or 30 different tables? The answer is that in general, for Postgres, join strategies can only work with 2 tables at a time. And so when you join multiple tables, you have to basically put parentheses around them so that you're just joining 2 things at a time. And the order that you do those joins in can have a really, really huge impact on your join performance. We're not going to go into detail about why, but if you're curious, there's some links. And in particular, this is an NP hard problem. So the best known algorithms for getting the optimal ordering run in exponential time, and we have no good ideas on how to make them not be exponential. For a small number of tables being joined, say like 3 or 4, what you maybe mostly do in practice, this isn't going to be necessarily a huge problem. But if you have like a really large database, you might be joining 20 different tables together, in which case you're not going to be able to find the optimal join ordering. This is one of the big open research problems right now in databases, is how do you get like good join orderings? And there's lots of practical considerations that Postgres and other databases take into account. So the fact that like merge joins, they require their input to be sorted, but they also output in sorted order, means that if you start doing one merge join, you can continue using merge joins. Or similarly, the hash step of a hash join, you don't have to recompute that for every one of the joins. So if you do a hash join once, you'll probably want to doing hash joins, because you can reuse that hash step, speeding up your future joins. In general, though, Postgres does a pretty good job at this, but the algorithms for actually doing this way beyond the scope of this class. This would be like, in order to start talking about these algorithms, you'd need multiple semesters of graduate level CS theory courses before you could even approach these problems. So the nice thing for us, Postgres Query Planner does a pretty good job automatically, and as long as you have good statistics on the underlying tables, it will pick a good join order. And if you just run that analyze command like we talked about before, it will give you those good statistics. Last big topic is parallelism. And the nice thing is that Postgres will automatically parallelize the vast majority of your SQL queries. In theory, all SQL queries can be parallelized. For various practical limitations, it's certain queries not yet parallelizable in Postgres, but devs are working on fixing this, and say 5 years from now, probably every SQL query will be possible to parallelize. The main thing that you have to know, I guess two main things to know for parallelism for this class in terms of grading are, the first one is that there's a small constant overhead to set up parallelism. So very small queries will not be parallelized. And say the Lambda server has the 80 different cores on it. A medium-sized query might choose to only use 10 of those 80 cores because of this overhead to set it up. But once it's set up, you get basically perfect parallelism. So that's the first thing that you need to know. The second thing is there's these references right here, and I might ask you on the exam basically arbitrary questions about parallelism from these references. So you have to be able to look up details in those references. There's a few minor concepts that they've come up as we've talked about the other things, so like multi-column indexes, the unique constraints, and the include statement. Those are things that you'll have to look up. And these things called expression indexes and partial indexes, those are also things that you will have to, you're responsible for looking up yourself in the documentation to see what those are used for and their limitations. And those can occur in arbitrary locations on the final exam, including these sort of free response questions. So these are things to make sure that you understand. Yeah, so concluding thought, creating indexes is important. It is how you get your queries to be fast. The sort of naive first level of database optimization is people creating just like an index on every column, thinking that's going to help, and it will help a little bit, but really you have to think a lot more carefully than that in order to get the most speed up for your queries. And the complicated queries are going to be requiring multi-column indexes, and you'll have to be thinking about sorting order and all of these other complicated things. Any questions about anything? Okay. Next week, what we'll be going over is you'll have another one of these Twitter assignments where you're going to have to be creating appropriate indexes for queries to make the queries actually fast on, we're actually going to be using like large amounts of the Twitter data now. So it'll be very important to get your indexes created correctly. And we'll also talk about, so far we've only talked about the B tree index, but there were these, all of these other types of indexes in Postgres as well, and we'll be talking about what they are and how they work. But that will be for next week. And so if there's no more questions, that's the end of class today, but if people do have questions, happy to answer them.
Professor Mike? Yeah, I was just wondering when is the final exam going to be?
Yeah, that's a good question. This question is, when's the final exam going to be? And everybody is going to have the same final exam. The seniors are required to have their grades in the last week of classes. The final exam will, I'll have the details exactly for you on Monday next week, but it'll either be take home over the weekend before grades are due, or it'll be on that Monday in person. Not sure yet which one's going to be the most appropriate.
Okay, thank you.
Question is, will it be in person? And that's what I have to decide, is whether it can be in person or if it can be take home. Yeah, so my preference is that it'll be take home so that there's no time constraints for everybody, but I'll have to just make sure that that works first. But yeah, I will have the details on that on Monday in class. Good question. Any other questions that people have? Okay, then I will see you all next week.